short column. In our previous videos, we have already discussed the basic rules for the design of RCC column as per IS 456. Also, we learned how to design axially loaded short column. Now, let's start to design the uni-axially loaded short column. First, let's understand what is uni-axial loaded column. You can see this in these two diagrams. These two diagrams suggest that when the column is subjected to either combined axial compression load and the moment, or the only axial load P which is applied at an eccentricity, so that the column is trying to bend about only one axis, is considered as the uni-axial load. See, in this diagram, P is axial load which is acting on the column and it is passing through the centroid of the column. Also, the moment is acting. Such type of column we can design as uni-axial loaded column. Or if a column is subjected with only axial load, but these axial load, if it is not passing from the centroidal axis, but it is acting at far from centroidal axis, it is considered as axial load with some eccentricity. Such type of column is designed as uni-axial loaded column. For the design of uni-axial load column, there are three sets of design charts are given in SP 16. Chart number 27 to 38. These are the first values of 12 charts for the rectangular columns having symmetric longitudinal steel bars in 2 rows for 3 different steel grades, for Fe 250 given, for Fe 415 and Fe 500. These charts are also bifurcated with D dash by D ratio values. So D dash by D values are given in the chart 0.05, 0.1, 0.15 and 0. Where the D dash is the effective cover of the column. Now let's see in SP16 chart number 27 to 38. See here is a chart number 27 which is on the page number of 112. It is saying that the compression bending chart with for the rectangular section of column reinforcement distributed equally on the two sides. And this chart is for Fy 250 and D dash by D 0.05. Now chart number 28 is for Fy 250 and D dash by D 0.1. Chart 29 is for 250 and D dash by D is 0.1 and so on. You can see each and every chart with a different values of Fy and D dash by D. Whenever you are calculating the uni-axial column with rectangular section having only two sides of the reinforcement, you have to refer these charts which is depend on the two values Fy and D dash by D. Second set of charts are charts 39 to 50. These chart values are for the rectangular columns having symmetrical longitudinal steel on the total 4 sides. It means all of the side, correct? Similarly with the grade of 250, 415 and 500. And each of them has the 4 different values of for D dash by D ratio, that is 0.05, 0.1, 0.15 and 0. Here is chart number 39 for the reinforcement distributed equally on the 4 sides for the rectangular section of the column, and these charts are also depending upon the values, different values of Fy, that includes 250, 415 and 500. Also with D dash by D values 0.05, 0.1, 0.15 and 0.2. Correct? If you see in SP16, these graphs are with the different colors. For Fy, all graphs are in black and white. For steel grade 415, all graphs are in red color, and the steel grade 500, all graphs are in yellow color, right? So you can easily find which graphs are for which grade, correct? The third set is for the circular columns. Charts 51 to 62. These charts are for the circular columns with the symmetrical longitudinal steel bars distributed equally on all of the sides. Similarly for the steel grade 250, 415 and 500, and with the D dash by D values 0.05, 0.1, 0.15 and point. Let's see for circular columns, right? Here is a compression with the bending for the circular section, correct? You can see in the diagram There is a circular column, and here's a chart from 51 to 62 for different grade of steel and different D dash by D values. Okay, so let's learn how to design uni-axial loaded column with example. Let's read the example. Design an RCC column having size 300 by 400 mm. It is subjected with factored axial force 1000 kN and the moment about the major axis is 150 kN into meter. Column unsupported length is 3.5 meter. Column is effectively held in position and not restrained against the rotation in both direction. Use M25 and FE 415. Here two conditions are given for the reinforcement in the column. One is column with two-phase reinforcement distribution and second is column with four-phase reinforcement distribution. Now let's start solution. See, the given data is written. Size of column is 300 by 400 mm. The unsupported length of column is 3.5 meter. Factored axial load is 1000 kilonewton and factored moment is 150 kilonewton into meter. We can use FCK 25 Newton per mm square and Fy is 415 Newton per mm square. The first step is to calculate the effective length of column. As per the example, the restraint condition is given for the column is the column is effectively held in position but not restrained against the rotation in both direction. Now let's see in the table for the effective length of column. We already discussed this in our previous tutorial. To understand the basic of the effective length of column, what is effective length, how to calculate effective length, you can watch these video and you can get the better idea. I will give link in description box and also I will give here I button. The restraint condition is given, the effectively held in position at both ends but not restrained against the rotation. The column is having pin connection at both joints. So the theoretical value and the recommended value both are same, and that is L, and that is nothing but the same, that is unsupported length of column. It means in this particular example, the value of effective length is equal to the unsupported length of column, that is 3.5 meter. It means 3500 mm. Second step is to determine whether this column is designed as short column or slender column. And how we can determine this? To calculate the slenderness ratio. The slenderness ratio, if it is less than 12 in both direction, then we can design our column as short column. And what is the formula for slenderness ratio? That L effective upon D or L effective upon B. It means effective length upon large lateral dimension or effective length upon least lateral dimension, right? See here in this example, see here we have written L effective, it means 3500 mm upon 400, that means D, correct? Okay, so here the slenderness ratio is 8.75, which is less than 12. And if we talk in terms of least lateral dimension, that means 3500 upon 300, value is 11.6. It is also less than 12. So we can say that we can design our column as short column. The next step is to check for eccentricity. For that, first of all, we have to calculate the design eccentricity, that is E. Now what is eccentricity? It is a distance between point of application of load to the centroidal axis of the column, right? As we know, the formula mu is equal to pu into E, that is moment is equal to force into perpendicular distance, right? Axial force is like this and moment is this, and definitely the moment is equal to force into perpendicular distance, right? We have both values of mu and pu, put the values and we can determine easily design eccentricity. The value is 150 mm, correct? Okay, now see here, always your design eccentricity should be more than E minimum. For uni-axial and biaxial types of column, the design eccentricity should be more than E minimum. Okay, now let's calculate E minimum. As per clause number 25.4 from IS 456-2000, we can determine the minimum eccentricity. The formula for minimum eccentricity is unsupported length of column upon 500 plus the lateral dimension upon 30. Okay, so if we consider E minimum for large lateral dimension, that is unsupported length of column, that is L, it means 3500 upon 500 plus 400, that is large lateral dimension upon 30. And the value is here 20.3 3 mm. Now for least lateral dimension 3500 upon 500 plus 300, that is least lateral dimension of the column upon 300 upon 30 is equal to 17, and this value is less than 20. You can see here this value 20.3, it is more than 20. When the value is more than 20, you have to consider only 20 mm. Okay, least value you can consider from both of these value. Correct? But here our design eccentricity is more than E minimum, so we are okay with the eccentricity. Our next step is to provide the reinforcement in the column. We have to calculate the main reinforcement and the lateral ties. If we talk about main reinforcement, then we have to calculate first the percentage of reinforcement in the column. In column, PT is denoted as small p only, and that is the percentage of reinforcement. How you can calculate the percentage of reinforcement for uni-axial column? As per SP 16, there are some charts are given for the column with the bending. From these particular charts, you can determine the percentage of reinforcement for the column. So let's see first these type of charts, how we can determine the percentage of reinforcement. From chart number 27, they are for compression with the bending. For the rectangular section, for the reinforcement distributed equally on two sides. These charts are depending upon these two values, Fy and d dash by d. The horizontal axis of the chart is for mu upon fck bd square values, and the vertical axis of the chart gives the value for the pu upon fck bd. Correct? Okay, but in this chart you can see also this curvature lines, right? So these curves will give the value for p upon fck. Here the small p is percentage of reinforcement. Okay, so to use these charts, first of all we require some values to calculate the value of p upon fck. And the values we have to calculate are horizontal axis and the vertical axis values. They are mu upon fck bd square and pu upon fck bd. So we have value for pu and mu, also fck and b and d, right? So let's calculate pu upon fck bd and mu upon fck bd square. Put all the values, and for this pu upon fck bd is 0.328, and for mu upon fck bd square the value is 0.125. For the charts, the other values are required, d dash by d and fy. What is d dash? D dash is the effective cover, that is we are assuming here 40 mm. Okay, so value of d dash by d is 0.1 and fy is given 415 Newton per mm square. Now as we know, we have to calculate the reinforcement for two different cases as per asked in our example. One is column with two-phase reinforcement distribution, and second with the column with four-phase reinforcement distribution. Okay, so let's see first for the reinforcement distribution on the two phases. Okay, now we have to use here SP 16 chart to determine the percentage of reinforcement in column. We require two values, d dash by d is 0.1 and fy is 415, right? Now we have to choose which number of chart we are going to use. So as I told you already that chart number 27 to chart number 50 we can use for the rectangular section. We just have to check in the chart whether it is for two side reinforcement or four side reinforcement, and also we have to check two other values, that fy and d dash by d. Okay, so for this particular example, let's see first the chart number 27 whether we can use this number of chart or not. Yes, we require first for the two side of the column, right? Now the other values we require, d dash by d is 0.1 and fy is 415. Okay, d dash by d 0.05, no. Also fy is 250, no. Let's go further. Yes, d dash by d is 0.1, but fy is 250. So we are not going to use this. Let's go further. No. Okay, now we just have to find, okay, and fy 415 is start from chart number 31. right? Here the d dash by d is 0.005. We are not going to use, but on chart number 32, yes, we are going to use this because it is for FY415 d dash by d 0.1 and it is for the reinforcement distributed equally on the two side, correct? Now how to use these charts and how to determine the required values, you can watch my these previous video. I will give link as I button here and you can also find the link in description box. Okay, so as per this calculation, we can find the value of P upon FCK is 0.075. Here we already know what is P. P is nothing but PT, or we can say the percentage of reinforcement. So the value of PT, that is 0.075 multiplied by FCK. Value of FCK is 25. It is 1.87 percentage. Correct? Okay. Now what is ASC? We know what is ASC. That is area of longitudinal section in the column. Okay. And we know the formula is PT upon 100 multiplied by B into D. That is percentage of reinforcement of gross cross-sectional area, right? And the gross cross-sectional area is B multiplied by D. Okay. So what is ASC? That is 2250 mm square. Now we have to choose one bar diameter or the combination of two bar diameter and provide the number of bars. Okay, and so I'm using here 4 number of 25 mm bar diameter plus 2 of 20 mm bar diameter, and for the arrangement of the reinforcement detail we can provide like this. As they asked the reinforcement distribution on two faces only, so we have to provide on two faces the reinforcement bar. First, the 25 mm size of bar diameter, there are 4, so provide them at the 4 corners of the column, and the other 2 bars are provided the center on the 2 sides of the column. Okay, in the lateral tie we are providing 8 mm bar diameter at 300 mm center to center, where 300 is pitch of the lateral ties, which is the spacing between two ties in longitudinal direction. Correct? Now for the second case, reinforcement distribution at on 4 side of the column. Now see the charts. For the 4 side of column, we are using from chart number 39. Let's see. No, we are not used 39 because it is for FY 250. Now let's see. Okay. From chart number 43, that is for FY 415, but D dash by D 0.05. Now let's go further. Definitely yes. Chart number 44, FY 415 Newton per mm square, and D dash by D we are using 0.1. Fine. We have these two values, mu upon FCK BD square and PU upon FCK BD. Right. So with this procedure we can determine P upon FCK from the inside curve 0.09. The value of PT, that is 0.09 multiplied by 25, that is 2.25%. ASC required is 2700 mm square, right? And here the reinforcement distribution will be on all of this side. Okay, and we can choose first, we can choose 1 bar diameter and then number of bars. So here I am choosing 8 number of 22 mm bar diameter equally on 4 side, right? So I'm providing 22 mm bar diameter, 1, 2, 3, 4, 5, 6, 7, 8 numbers. Use 8 mm bar ties. Now let's calculate for the lateral ties. In lateral tie, for the bar diameter, the criteria as per IS 456 are 1/4 of the main bar diameter. Bar diameter is 22 mm, right? That is 5.5 mm. Second is 6 mm. We can use larger than 2 values, and I am directly using 8 mm bar diameter of the tie. And for the pitch, that is the spacing of the lateral ties. There are 3 different criteria. We can use least value from these 3 categories. First is least lateral dimension, then 16 multiplied by bar diameter, whichever is maximum bar dia, and third one is 300, and we can use the least value. So provide 8 mm bar diameter at 300 mm center to center lateral tie.